We have already stated that the critical altitude is the altitude above which the selected boost or manifold pressure can no longer be maintained. As the aircraft climbs, to maintain the required pressure in the inlet manifold, the turbine and the compressor must be driven faster and faster. To ensure that this happens, the wastegate progressively closes. Once the wastegate is fully closed, which happens at the critical altitude for that engine and turbocharger, if the aircraft continues to climb, the manifold pressure can no longer be maintained above that altitude. The wastegate may be controlled manually by the pilot, but most turbocharger systems have an automatic control fitted to prevent overboosting of the engine. In an automatic control system, the wastegate is mechanically connected to a piston situated within an actuator. The position of the piston depends on the opposing forces of a spring and engine oil pressure. Spring force tends to open the wastegate, and oil pressure tends to close it. Thus, oil pressure in the actuator regulates the position of the wastegate according to engine requirements. Various controllers may be used to vary the wastegate actuator oil pressure. These are some of the types of controller which can be used. Absolute pressure controller, variable pressure controller, differential pressure controller, density controller, rate of change controller, pressure ratio controller. We will initially concentrate on the absolute pressure controller. Earlier we mentioned that some simple turbocharger systems use an absolute pressure controller. The absolute pressure controller is designed to limit compressor output to a preset value by means of a wastegate actuator. A diagram of this type of controller is shown here. The absolute pressure controller uses an aneroid capsule, which is sensitive to compressor outlet pressure, to control the oil bleed away from the wastegate actuator, thereby controlling the wastegate position to maintain the required compressor outlet pressure. The throttle valve is then responsible for controlling manifold pressure. At low power settings, full oil pressure is applied to the wastegate actuator, which closes the wastegate and diverts all the exhaust gases through the turbine to maintain the compressor outlet pressure at the designed value. The oil, which is used to move the piston in the wastegate actuator, is taken directly from the engine lubrication system. This oil is also used to cool and lubricate the turbocharger bearings. When the throttle is opened, the engine RPM is increased. This produces an increase of exhaust gases, which increases the supercharger turbine and compressor speed, and this results in an increase in compressor outlet pressure. As the predetermined outlet pressure is approached, the absolute pressure controller capsule is contracted, which opens the bleed valve to bleed oil away from the wastegate actuator. This allows the actuator spring to open the wastegate and divert some of the exhaust gases away from the supercharger turbine. The supercharger speed is reduced, and supercharger outlet pressure is maintained within the predetermined limit. As the aircraft climbs to altitude, the air density decreases, and compressor outlet pressure reduces. This causes the APC capsule to expand and close off the wastegate actuator oil pressure bleed valve. With increasing actuator oil pressure, the wastegate is progressively closed, and more exhaust gases are directed to the turbocharger turbine. This increases both the turbocharger RPM and compressor delivery pressure, thereby maintaining the selected manifold pressure. Eventually, the wastegate will be fully closed, and the aircraft has reached critical altitude. Above this height, both manifold pressure and engine power output will drop off, despite the turbocharger operating at full speed. Coarse use of the throttle may cause a phenomenon called throttle sensitivity to occur. Throttle sensitivity is a result of a chain of events which can occur as a result of change of throttle position. Let's imagine what might happen if the pilot opens the throttle in a simple system with an absolute pressure controller like the one just described. Initially, the inlet manifold pressure will rise. The absolute pressure controller will sense a drop in compressor output pressure, and the aneroid capsule will expand to close the oil bleed valve, increasing the oil pressure in the wastegate actuator. The wastegate will close in response. The new wastegate position diverts more exhaust gas to the turbine, which accelerates. Compressor output rises in response to the increased turbine speed. As a result, the inlet manifold pressure will rise again, and so on. The result is that the turbocharged engine's boost or manifold absolute pressure setting will require frequent adjustment, particularly if the pilot moves the throttle valve quickly, not waiting for the system to stabilize before making further adjustments to the throttle. The use of a differential pressure controller will help to control these unstable conditions, which are sometimes called bootstrapping. Bootstrapping occurs during part throttle operation, and it's an indication of unregulated power change that results in a continual drift of boost or manifold absolute pressure. It's an undesirable cycle of turbocharging events, causing the boost or manifold absolute pressure to drift in an attempt to reach a state of equilibrium. This diagram shows the differential pressure controller and a density controller being used to control the position of the wastegate. This is a more sophisticated system than that which simply uses the absolute pressure controller. The differential pressure controller is used to reduce the compressor output pressure during partial throttle operation. The differential pressure controller senses the pressure drop across the throttle. If a lower than maximum manifold pressure is required, the differential pressure controller will adjust the wastegate position to maintain a differential pressure of approximately 2 inches of mercury between the compressor outlet, deck pressure, and the inlet manifold. As previously stated, the differential pressure controller is used to control compressor output pressure during partial throttle settings. At full throttle settings, it would have reached its maximum controlling limit, and will no longer be capable of controlling wastegate operation. As a result, a density controller is usually installed as a safety backup to the differential pressure controller. The density controller limits the maximum manifold pressure and maintains compressor outlet density to that required for full power at full throttle settings up to critical altitude. The density controller is fitted with a capsule filled with dry nitrogen, which is sensitive to both compressor outlet pressure and temperature, and therefore its density. The capsule increases the compressor outlet pressure to compensate for the drop in charge density which results from a temperature increase caused by the compressor working harder as the aircraft climbs. Having a density controller will ensure that maximum available density will increase up to critical altitude. By so doing, the density controller will reduce the losses normally associated with charge temperature increase, and thus density decrease, which would otherwise occur as the aircraft climbs. Either the density controller or the differential pressure controller will be in use and controlling the wastegate position at any one moment. Another type of single controller system is the variable pressure controller, which is similar to the absolute pressure controller, but has a cam mechanism interconnected to the throttle linkage. The cam adjusts the setting of the oil bleed valve as throttle position is varied, thereby controlling wastegate position to provide a manifold pressure relevant to a given throttle position. The controller capsule will continue to adjust for changes in altitude.